Okay, so let's talk about problem number 7. So here's this Lagrange point question. I'm going to get you started on it so that you're not just completely like, "Wah." So this is what I just showed you. Here's the Earth. Here's the moon. And we're going to try and find 2 points, L1 and L2. Okay, these 2 Lagrange points. So, L1's the simplest one to visualize because it's like the mid-ridge in between 2 gravitational wells. But here's where this idea starts, is that the gravitational force between the Lunar Command Module and the Earth at some point has to equal the gravitational force between the Lunar Command Module and the moon. Okay? At this L1, this is what's going to happen. Okay? The gravitational force towards each one is going to equal out. Okay? Got the idea? Mm-hmm. All right. So, you got to go old school Newton to start this problem. So, this is going to be big G, the mass of the Lunar Command Module, mass of the Earth. Now, this is going to be some distance x, okay? We don't know what the distance is, okay? We don't know what it is. Don't care what it is. We're just going to let that be x. But that's going to get squared, okay? Because it's Newton's law of motion, right? Now, that has to equal big G, the mass of the Lunar Command Module times the mass of the moon, okay? So in this problem, I tell you that the distance from the Earth to the moon is 3.844 times 10 to the 8th meters. So that's the distance from the Earth to the moon, okay? So if this distance is x, what's the distance between the Lunar Command Module and the moon?
Yeah. What's the top, that 3.844, is that to the moon or the?
Yeah, that's the distance from the Earth to the moon.
You drew it to like the Lagrange point.
No. That's just this from the Earth to the moon.
The total distance minus x.
Yeah, the total distance minus x. So what's left over is the total distance minus that first distance. Okay? Makes sense? Okay, cool. So this distance is going to be 3.844 times 10 to the 8th meters minus x quantity squared. Okay? That's going to be important. It's going to be squared. Now, when you look at number 7, why didn't I give you the mass of the Lunar Command Module? Cancels out. That's why you don't have that number. Okay? What happens to big G? Cancels out. Cool. This is why you work these with variables first. Okay? Now, you all know my feelings towards fractions, so I'm going to cross multiply. So I'm going to take the mass of the Earth times 3.844 times 10 to the 8th minus x quantity squared is going to equal the mass of the moon times x squared. Okay? Cool with that? Got it. Mm-hmm. Now, you're given in the problem, or up above, that the mass of the moon is 7.35 times 10 to the kilograms. Okay? So I'm going to divide both sides by the mass of the moon. Okay? So the mass of the moon cancels out. Okay? So somebody take the mass of the Earth, which hopefully you have stored in your calculator. Take the mass of the Earth and divide that by the mass of the moon, which is 7.35 times 10 to the 22nd. And in case you haven't figured out, don't type in times 10. Use that EE key. That's going to save you a lot of hassle. Because if you type in the times 10, that really messes up your order of operations. So what do you get when you take the mass of the Earth divided by the mass of the moon?
81.3,
Give me one more digit.
81.35.
81.35 times 3.844 minus x squared equals x squared. Okay, now, at this point, you have a decision to make, okay? You have a decision to make. So let me show you the two ways you can do this. So let's start with something simple. Let's say that you had 5 minus x quantity squared. Okay, so let's go back to algebra 1 days. What do you get if you square 5 minus x quantity squared?
X squared minus 10x plus 25.
Plus 25, right? You ready to remember that? Come back to you?
Yeah.
So one option is that you expand this value, okay? And you do just what Gavin did. You take the 3.844 times 10 to the 8th, square that to get that value, multiply it by 2 to get that, and then you're going to have your x squared, okay? Then you're going to distribute 81.35 over all of that, okay? But that's still going to equal x squared. Now, eventually you want to use the quadratic formula. To use the quadratic formula, what does one side have to equal?
0.
0. So then you got to subtract an x squared over here. So option number 1, you expand this binomial. You multiply it by everything by 81.35.
Right.
You move the x squared over and then plug that into negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay? It's the quadratic from the depths of Hades. Okay?
Yeah.
But if you really want the challenge of doing a very, very, very hardcore quadratic, that's cool. Option 2. Option 2. Could I take the square root of everything?
Oh my goodness, you can.
Oh.
I like that option.
So, what's the square root of 81.35?
Around 9.
Around 9. But it's plus or minus, what do you get? I need the actual number. Square root of 81.35.
9.0194.
So 9.02,
Yeah.
okay? Equals x, okay? So here's how you get your two solutions, okay? Here's how you get your two solutions. You take positive 9.02 and you distribute positive 9.02. So you get 3.844 times 10 to the 8th times 9.02 minus 9.02x equals x. And then you just solve it like a simple one variable equation. You get x on one side, so you get the numbers on the other, and you solve for x. Okay? The second solution is going to come when you repeat the same process, but you start with negative 9.02. You distribute negative 9.02 over this, move all your x's to one side, solve for x. Okay? This turns into just an algebra problem versus a quadratic. How you solve the problem, I don't care. But here's what you should see. Here's the Earth. Here's the moon. L1 is going to put you inside the radius of the moon's orbit. Okay? L2 is going to put you on the other side of the moon's orbit. So obviously one answer should be less than 3.844 times 10 to the 8th. The other answer should be bigger than 3.844 times 10 to the 8th. Okay? Now, there's two parts that you need to answer. You need to find L1 and L2, And then here's a subtle question that everybody tends to ignore, because you're so happy that you found L1 and L2, you forget to answer this question. And then I say, once the limb crosses L1 as it approaches the moon, what will happen to its velocity? Will it increase, decrease, stay the same? And why will it increase, decrease, or stay the same? Okay? So don't forget to answer that subtle part of the question. So on number 7, you can just start from here. If you want to show the steps to get to that point so you understand it, that's great. But at least start from here. Okay? Understand where it comes from. But mathematically, you can start right there. Okay? Cool with that. All right. So, let's talk about number 9. So on number 9,
Wait, I have a question.
what?
What causes L2?
It's the same idea. Like, if you could put it here, the combined pull of the moon and the earth, because you're further out, so the moon and the earth have like a weaker gravitational pull on you, especially the earth. So if you park it out here, the combined gravitational pull of the moon and the earth would provide the centripetal force to keep it in orbit. So here, it's a tug of war between the two of them, okay?
Yes.
Out here, you're not in tug of war. Both of them are pulling in the same direction,
Yes.
but the pull from the moon is a lot less
Pull from Earth.
because of the fact that you're so much farther from the moon once you get out there.
So like the gravitational pull is just so little that it doesn't even matter.
Yeah, I mean it does, but not relative to the moon's.
Oh,
But it's the combined pull of both of them is what's going to create that centrifugal force to keep it moving. That's why there's two Lagrange points. Okay,
so confusing. But
when you get to question number 9, let me kind of give you a visual of what's happening on number 9. So here's our rock. And one of the things we figured out that basically allows your modern existence to happen, and most likely that your folks can track you on Life 360 and see exactly where you're at, is the fact that we have a parking lot of what we call GPS satellites, okay? Geopositioning satellites, GPS. So these satellites are in what we call a geosynchronous orbit. So what happens, like the math that we did, like when we launched Caitlin into orbit, and her orbital period was like every hour and a half, okay? Boom, every hour and a half, going around there. Well, that wouldn't work for geopositioning satellites because everything's moving relative to each other, okay? You're moving, the satellites are moving, it's a nightmare. But what happens with the GPS satellites, you park them way out here. So that way, when you're here in Maze America, there is a satellite parking lot of satellites that aren't moving relative to you. So these satellites are parked out here so that you can triangulate your position. So what's happening is that your phone is continuously sending a signal to these satellites. And what it's doing is that it's keeping track of the distance in the time between this satellite, that satellite, and the third one. And based upon the difference in times when those signals get there, that's what allows it to figure out where it is. So it's somewhat analogous to, like, let's say Dylan's in the back of the room, and I'm in the front of the room, okay? And Vanessa is in the middle. She's in the dead middle of the room. If Dylan yelled and I yelled, and we both yelled at the same time, she would hear both of our voices getting to her at the same time because they're traveling the same distance. Now, if she was closer to Dylan, and Dylan yelled, and then I yelled at the same time that Dylan yelled, she would hear Dylan's voice first, and then she would hear mine. So if she knew the difference between when those two signals arrived, she could figure out where she is. Like, oh, I heard Dylan's voice 0.2 seconds before I heard Mr. Burkamp's voice. Oh, okay. Speed of sound is 330 meters per second. That tells me this is how much further I am from Mr. Burkamp than I am from Dylan. So we do the same thing, but we use radio signals. Radio signals conveniently travel at the speed of light, which is 3.00 times 10 to the 8th meters per second. So it travels really, 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 really fast. So the first thing that you do on number 9, you want to figure out the orbital radius of these planets so you know where to park them in this orbit. So what you need to do on number 9 is that you need to start with that big Swiss Army knife equation that says 4 pi squared r cubed equals big G mass of the Earth t squared. Okay? Is that the mass of the satellite?
No.
No, it's the mass of the Earth because that's what you're orbiting. Okay? You want the orbital period to be 24 hours. Okay, so then you're going to have your value of t. The only thing you're not going to know is r. Okay? So you need to solve this equation for r. Big G m t squared over 4 pi squared, and then take the cube root of that. Now, here's what's important. This r, when you get it, is the distance from the center of the Earth out to where that satellite is. Now, when you actually use your phone, you're not in the center of the Earth. Where are you at?
Surface of the Earth.
You're on the surface of the Earth. Okay? You're on the surface of the Earth. So the actual distance that your phone is going to use to get this location is from the surface of the Earth out to that point. So if this distance gets you from the center of the Earth out to that satellite, how are you going to get the distance above the Earth?
Subtract the radius of the
Yeah,
Earth.
subtract out the radius of the Earth. So your answer to 9A should be something times 10 to the 7th. Okay? This is after you subtract out the radius of the Earth. Okay? Still going to be times 10 to the 7th. So then, on B, I'm saying, and the reason that I put B on there is that when you talk about distances to orbits, it's tough to reference that in terms of like a scale that we're used to dealing with. Okay? So what I said on B is that, okay, if you're going to drive from Wichita to Kansas City, and y'all can kind of visualize what that distance is, okay? That's 317,000 meters, 3.17 times 10 to the 5th meters. So all I'm asking you to figure out is like, okay, how many times greater is the distance to that satellite than it is to the distance from Kansas City to Wichita? Okay, so it's just a relative value. It's like, oh, okay, well, how far is that? So then, on C, I'm saying, okay, the speed of light is 3.00 times 10 to the 8th meters per second. How long would it take for a signal to travel from your phone to the GPS satellite orbiting above you? So, what I want you to realize here is like, okay, this is a long way out, okay? Just like 10 to the 7th meters. Order of magnitude bigger than the radius of the Earth itself. You're not to the moon because the moon is like 10 to the 8th, okay? So you're an order of magnitude less than the distance to the moon. But you're still a long way out there, okay? Much further than like what the International Space Station does and things like that. You are out there a long way. So what I'm trying to get you to see here is like, okay, how long does it take for your phone to communicate with that satellite that's out there almost between halfway between the Earth and the moon, okay? Traveling at the speed of light. And what you'll see is that if you do this right, your answer to 9C should be around 1/10 of a second, okay? Which is about that long. So when your phone communicates with that satellite, that signal from you to the phone takes about that long. Satellite gets that signal, processes it, sends it back. So that communication between your phone and that satellite to send the signal out, send that signal back, that long. Okay?
My goodness.
So that's the beauty of light traveling as fast as it does. So this is why you can get real-time data that shows, oh, here's where I am, right? Even if you're driving down the road, it's like, oh, right, this is exactly where you're at, because that communication is so fast because the signal travels at the speed of light. Okay, so there's that. Now, speaking of the International Space Station, when you get to number 10, so on number 10, it's the same idea. I'm telling you that the orbital period is 90 minutes. So now you want to find, again, the distance from the center of the Earth out to the International Space Station. Okay, so instead of an orbital period of 24 hours, you're going to have an orbital period of 90 minutes. Obviously, your answer to that should be a lot less than your answer to the GPS satellites. Okay. When you get to some problems out of the book, so let me give you some hints on some of the problems out of the book. When you get to, I think it's 57. Yes. So when you get to number 57, let me give you a visual on 57. So this is what we call a conical pendulum. So on a conical pendulum, instead of just going back and forth in the same plane like this, on a conical pendulum, it's going around in a circle like this. Okay? That's what you got going. So, as this goes around in a circle, if I were to stop this right here, okay, freeze it right here, it's coming around. What are the two forces acting on this rubber stopper? There's only two.
Tension and
Tension
gravity.
on the string.
Gravity.
Gravity's trying to pull it down,
Centripetal.
and what else?
Centripetal.
Nope.
What?
Tension of the string.
Tension in the string. That's it.
What?
We'll get to what you're talking about in just a second. So as this thing is sitting here like this, going around in a circle, the only two forces that are actually acting on it are gravity and the tension in the string. Okay? That's it. Those are the only two. Now, it's simple to calculate the gravitational force. That's old school mg. Not a big deal. That's the easy one, right? Now, the tension is problematic because here's what I want you to visualize. What if this was just hanging straight down? What would the upward tension in the string equal?
Force normal or
Yeah, or the gravitational force, right? It's balancing it out. So even if it's out here like this, the vertical component of that tension still has to balance out the gravitational force.
Oh no, they're just horizontal.
Ah, what's the horizontal force creating? You said it earlier.
The centripetal force.
No, what'd you say?
What a centripetal force.
Yeah. So the vertical component is balancing out the gravitational force. The horizontal component is creating the centripetal force.
Wait. So then how is there no centripetal force?
There is. That's the horizontal component of tension.
You said there was only two forces.
But there's components
Oh. Okay.
of the tension,
Oh, okay.
okay? The actual true forces are only tension and gravity.
Oh.
But the tension is made up of two components that result in that overall tension,
Oh. Okay.
okay?
Mm-hmm.
So if you look on number 57, you got a 500-gram ball. Oh, that's easy to find your gravitational force. The string is 1 meter long, okay? And you're told that it swings in a horizontal circle with a radius of 20 centimeters. So let me give you a hint. Find that angle, okay? Once you find that angle and you know that it's a 500 gram mass, and then you're gonna know the vertical side of that triangle,
Kate,
then it just turns into a trig problem. Okay? So if that's 500 grams, that means that's 4.9 newtons. So if this is 4.9 newtons and you're trying to find the tension, which is the hypotenuse, what does your answer have to be greater than when you find the tension?
7.
Well, it has to be greater than 4.9
Okay, yeah.
because you're finding the hypotenuse.
I got it.
Okay?
This one's easy, right?
Now, when you get to 57B, the book gives you a jacked up answer of revolutions per minute. On 57, the answer in the back of the book makes no sense, okay? Just find a velocity, and here's how you can find the velocity, because once you find the horizontal component, you know it's centripetal force equals mv squared over r. Then you're going to know the horizontal component of that force, which is your centripetal force. You're going to know the mass, you're going to know the radius, find the velocity. Okay? So that's just kind of a big hint on that one. Let me see what else. On the problems that I gave you, on number 8, when you're going to try and find the mass of Saturn, that should be something times 10 to the 26th. Your answer to 10A should be something times 10 to the 5th.
10A, 10 to the 5th.
Yeah. But 9A is to the 7th. So 9A is to the 7th. 10A is to the 5th. And on 13, because that all hinges off each other, on 13, this is where electromagnetic force meets gravitational force. So if all goes well, when you get done on 13C, you have to find the mass of the proton to create enough gravitational force to hold the electron in orbit around it.
What?
So it all kind of hinges off each other. But if all goes well, your answer to 13C is going to be something times 10 to the 12th.
Oh my goodness. Was that like a velocity or something?
Now that's the mass of the proton to keep an electron in orbit around
Wait,
it.
so 10 to the negative 12 or 10 to the 12?
No, 10 to the 12th.
It's a big number for the mass of the proton.
Proton?
To create
Okay.
the same amount of gravitational force as electromagnetic force.
Oh, yeah, that makes
Okay?
Just saying how electronic.
Yeah. So if you're going to just try and decide, wow, how much time is this going to take? So let me give you some perspective. So here's my assignment. This, and that. Okay? So that's how much space it took me to work all these. So if you think, oh, I'll just crank this out in like 10 minutes, ain't happening. This is why this is not due until Thursday. Okay? This assignment takes quite a while. So I'm just telling
So
you.
you're
straight
telling
up.
me-
This before Wednesday night?
I would.
Start at Wednesday morning.
So tomorrow, tomorrow, if you have any specific, if you've looked over these, I would suggest you at least look over the problem, and if there's one you go, my God, I have no idea how to start this, I would suggest that would be the time, because we don't have school on Wednesday, and the test is on Thursday.
Will you be here Wednesday?
I'll be here, but I gotta do testing.
Could you help us anyways?
No, it's AC.
You're not
testing.
coming
He
to
can't
school.
help us. Like, he's busy.
You're a senior.
Yeah, I've gotta be proctoring a test. Now, I'd be here in the
I'll be
afternoon,
here though.
but not in the I'll be here all day.
Oh,
If you want to come in the afternoon, that's cool. That I could help you, but not during the morning.
How does that work? Do we go to our flex teacher or what?
When?
Do we go to?
No,
Wednesday.
they randomly.
No, they assign you
yeah,
rooms.
they'll give you a room.
There'll be a poster, usually in the front, that says, here's where you go.
I think I'm gonna be.
I bet you'll be in the.
Okay.
all day.